As an introductory chemistry student, there will likely be a point in your academic or professional career where you will have to prepare a buffer solution. A buffer is a solution consisting of a weak acid and its conjugate base, or a weak base and its conjugate acid. Together, these species work to maintain a designated pH for a system by buffering against additional species that could cause pH changes. Today, you will learn how to make a buffer in the laboratory. As an example, we will be preparing 1 liter of a 100 micromolar acetic buffer at pH of 4.5. The materials we have are a 1000 milliliter beaker, a 500 milliliter beaker, a 10 milliliter graduated cylinder, a 100 milliliter graduated cylinder, a stir bar, a stir plate, and a pH meter. The chemicals we will be using are acetic acid and a 1 molar sodium hydroxide solution. First, we must calculate the amount of acetic acid we need to make the solution 100 micromolar. To do this, we use the molecular weight to solve for the mass of acetic acid needed, then use the density of acetic acid to solve for the volume needed. In this case, we need about 5.72 milliliters. Place the beaker onto a stir plate and add the stir bar into the solution so that it mixes well. Add about 800 milliliters of distilled water to the 1000 milliliter beaker. Then measure out the required amount of acetic acid and pour it into the beaker as well. We will soon be adding the sodium hydroxide to the solution until the pH reaches our desired level of 4.5. But to help us refrain from adding too much, it is always helpful to perform calculations to determine just about how much volume is needed. To do this, use the Henderson-Hasselbalch equation with the desired pH, the pKa of acetic acid, and the moles of acetic acid to solve for the moles of sodium hydroxide needed. In this case, we find that we will need about 35.5 milliliters of sodium hydroxide to reach our desired pH. Insert a pH meter into the solution to keep track of the pH level. Then, carefully add sodium hydroxide until the pH meter reaches the desired pH level. You may find that you did not add exactly the amount of sodium hydroxide you calculated, and that is normal due to the effects of ionic strength on pH. Once completed, dilute this solution to 1 liter with additional distilled water. Then remove it from the stir plate. You have now experimentally created your very own buffer solution to be used in a wide variety of applications. The process outlined in this instructional video can be used to prepare buffers of different pH levels from other acids as well. Buffers can also be prepared from weak bases in the same format, except that hydrochloric acid should be added to the solution instead of sodium hydroxide.
The bicarbonate ion in blood is extremely important in the blood buffering system. As the concentration of hydrogen ions increase, bicarbonate reacts with it to form carbonic acid. This reaction prevents blood from becoming too acidic and keeps the ratio of carbon dioxide to bicarbonate relatively constant. This is because as you are exercising, the amount of bicarbonate decreases because it is taking up hydrogen ions, because the change is slight compared to the amount of bicarbonate and carbon dioxide in your body. The change of pH is not significant. This buffer is not the only way we control the pH of our blood during exercise. Blood is pumped throughout the body by the heart, and it is carried to the lungs, where carbon dioxide is taken from the blood and exhaled. In contrast, the buffer is also used in the opposite way if the blood pH is too high. Carbonic acid gives up hydrogen ions to form bicarbonate, which increases the concentration of hydrogen atoms and increases the pH. Another way the body prevents the pH from being too high is by removing bicarbonate from the bloodstream throughout the kidneys.